so hot, right? Whatever, right? It reminds you of those, like fragrances. I married my high school boyfriend. Fragrances remind you of things, right? They bring about your memory and they spark emotions. So the limbic system is strongly linked to the olfactory, right? So, and it bypasses the thalamus. There's no thalamus in the way here. There's no relaying at all. It goes straight to your limbic system. It then can branch from there and go to other areas. So from the limbic system, it can go to the thalamus. From the limbic system, it can go to the hypothalamus. From the limbic system, it can go to the prefrontal cortex, right? This is your personality and your logic, right, and your decision making. Right? Oh, this smells like my old boyfriend. Oh, I should call him. Oh, no, I should not call him. Right? That's your prefrontal cortex making that decision. And then other limbic system components, those emotions, those memories. You might even experience like a psychosomatic effect where your pupils dilate or your heart rate quickens or slows down or maybe you start to feel nauseous, right? Things like that because of the limbic system interplay. That smells influence a lot of what we do and how we act. And our response can lead into something like eating. Imagine that I assume most of us haven't ate dinner because our class starts at 5, so you probably didn't eat dinner before class tonight, so maybe you're feeling a little hungry right now. So if someone was in the back of the classroom popping popcorn, right, or cooking bacon, maybe even just saying those words makes your mouth water, right? That's exactly what, imagine smelling it. You would smell it, you would smile, oh, I'm so hungry right now, I really want to eat, right? Limbic system. From there, your hypothalamus is going to say, yeah, buddy, I can't wait to eat. Your hypothalamus, your homeostasis center, that's going to get all your digestive juices and all those things flowing and ready for when you eat, right? Eating, a lot of our digestive process actually happens before we eat. You'll see that in AP too. It's pretty cool. So anyways, I would do something like this for all of those pathways so that you understand how they work. Balance, this is all done through what's called the vestibular system, right? So this is part of your inner ear. Having those senses, we'll look at how that works in our special senses, going right to the cerebellum, right? All of that vestibular stimuli goes right to the cerebellum, giving information. And from there, then it can go to the thalamus, then it can go up to your cerebral cortex. So, voluntary movement takes things a step further. So that was all sensory information coming in. Movement going out, right, descending, efferent fibers. This is all a little different. This is going to include cerebral cortex, basal nuclei. This is also going to involve the spinal cord and the cerebellum. So there's different parts of our nervous system that are going to come into play and interact when we're talking about movement, right? And all of this is geared towards skeletal muscle contraction, right? We need to move our arms, move our legs, adjust our back muscles, our neck muscles, right? All of those things, right? So we have upper motor neurons and lower motor neurons. We drew those already on the dude that I erased, right? He was over here already. The interneurons are always that in-between messenger, deciding exactly which motor neurons are going to fire, which motor neurons are going to be activated. Lower motor neurons are the ones that leave the central nervous system and go out to the peripheral effectors, right, those muscles. That was all in that drawing that we did. So there's some tracks involved. The corticospinal tract, from the cortex to the spine. Corticonuclear tract, right? These involve our cranial nerves, which we haven't talked about yet. But the cranial nerves are nerves that come directly off of our brain. They mostly come off of the medulla oblongata, the pons, and the midbrain. Some of them are sensory, most of them are motor. Right? So motor fibers coming directly off of the pons, directly off of the medulla oblongata, are all part of this corticonuclear tract. The corticospinal tract. This pathway involves that crossing over, right? Upper motor neuron crossing over, lower motor neuron leaving. Right? And so a lot of times, sometimes these will actually cross over in the midbrain, sometimes they'll cross over in the pons. They usually cross over up in the brain as opposed to down in the spinal cord. Right? And so these form those corticospinal tracts. We'll look at what they are. Not all of them cross over. A small percentage of them do not, but most of them do. Right? So initiating from that primary motor cortex, which has a homunculus, just like the primary sensory cortex, right? Kind of a map of all of the body parts, firing down, crossing over somewhere in the brainstem, getting off to the other side of the body, right? Going off and going to the skeletal muscles distributed throughout the body. Upper and lower. The we just did this. All right, corticonuclear tracts, these don't cross over because these come directly from the cranial nerves, right? They're going to travel directly off of the brainstem. So we'll talk about the cranial nerves in just a little bit, but they do not cross over because they're literally coming right off of the brainstem itself. So, simple movements require a very concentrated effort of groups of motor neurons working together to create a very simple movement. We call that a motor program. A motor program is kind of like, okay, I'm going to decide to walk now. My body automatically knows which muscles to contract, right? Which muscles to flex, which muscles to extend. It knows that because I formed a motor program. The first time you do an action, right? If you were to come up here and teach me like a new hip hop dance routine or whatever, it would take me a while to figure that out because I don't have that motor program, right? Maybe you do, right? So the motor program is the group of motor neurons that work together to coordinate some type of effort, right? So this is going to involve the basal nuclei, which are those background patterns of movement. It's going to involve the cerebellum, and it's going to involve parts of the motor association areas, right? Your primary motor cortex. So your cerebral cortex in all of this is planning, right? It's making you consciously aware of the fact that you're going to walk across the room. You feel the fact that you're walking across the room. Your cerebral cortex is always conscious awareness, right? Upper motor neurons send those signals down. That's always the first step. They decide we're going to flex the hip flexors, right? We're going to lift our leg. In that was a conscious control movement. It's all done from the motor homunculus, just like the sensory homunculus. Same idea. It's in ratio and proportion to the amount of motor neurons for an associated area, right? And so this is your motor homunculus, right? It's a lot different than our sensory homunculus. Notice how big the hands are, because our hands have lots of very fine motor skills associated with them. If you've ever watched a 2-year-old try to hold a crayon and do something compared to us, right? Even though our drawing skills might not be that good, we still have much higher level of control than a toddler, right? And that's because of those motor skills, right, that come about. Lips and tongue, same thing. Lots of fine movements going on with those. What about our calf muscles? Right? What do? They flex. So they can't. You can't like smile with them. You can't like wiggle them around. Like they just are that, right? So there's different parts of our body that have different levels of motor control. And so the basal nuclei are there for that background level of control, that background pattern of big movement so that you can do all of the fine things, right? I can walk around, I can run, I can do all of these established patterns without really having to think about where my feet are, where my knees are, where my hips are, where my body is in space. It just naturally happens. The substantia nigra assists with that, right? We mentioned that before. The substantia nigra works along with the basal nuclei to establish those background patterns of movement. You don't have to know the different names of the basal nuclei, right? But it's a couple groups of nuclei based in the white matter of the cerebrum. But they're there to set those background movements, right? It can inhibit some of the movements that might interfere or impact the background movement that you need to continue. So, initiating is not what your basal nuclei do. Your basal nuclei don't initiate, your basal nuclei continue. Your cerebral cortex has to initiate. I'm going to initiate walking, but now my basal nuclei have taken over, right? And initiation is not what your basal nuclei do. Your basal nuclei are there for the background pattern. This is just going through the different nuclei involved. Damage to your basal nuclei can be detrimental to your movement, right? So ability to initiate walking and ability to inhibit any stumbling or tripping or kind of dragging of the feet, those types of things involuntarily, you won't be able to, and I'm just using walking as an example, but talking is another kind of motor skill that is very fine-tuned and you don't have to think about anymore, partially controlled by your basal nuclei. So lots of things like that. The cerebellum is going to play a role in kind of continuing the moment and adjusting, right? So your cerebellum's consciously monitoring all of these things, all of your movements, all of your contractions, your balance, right? Along with your vestibular nuclei, right, the ones that are in control of your balance, your cerebellum takes all of those things into consideration to know how to adjust your body position, right? Have you ever watched like a squirrel like run across a fence or like run across a tree and how its tail just kind of moves back and forth, kind of goes this way or that way or stands straight up? That's kind of what your cerebellum's doing all the time. It's adjusting, finally, your muscles, right? To stand on one foot takes a lot of hemming and hauling on both sides of your supporting leg. Your cerebellum does that for you. So you don't have to consciously think, oh, I'm shifting more to this side, oh, I'm shifting more to that. Your cerebellum is constantly readjusting the sails, so to speak. And so that's what it's doing, right? It's taking all of that information into consideration. Can help you overcorrect. So the cerebellum, always getting information from the cerebral cortex and the motor neurons that are contracting consciously, always getting information from your vestibular nuclei, right? Your balance nuclei, the ones that are controlling where your balance is, and always getting information from the sensory, always getting information from the actual muscles. Your muscles themselves have little sensory neurons, sensory receptors in them that tell your brain how contracted and how tense they are, and we'll look at those eventually. So your cerebellum is taking all of that into consideration when thinking about how balanced you are. Let's try to wrap up this little section right here, showing you that information coming in, and a lot of it is going into the cerebellum, and then the cerebellum can take that information and make you consciously aware of it. Right, that primary motor cortex. That's that last little piece. So that's showing you the big picture of all the fine motor control, right? Motors all descending, coming down, crossing through that thalamus, coming out, crossing over the brainstem, out to your skeletal muscle. We did it. So, your quiz on Tuesday covers all of this.